which is called Stokes' theorem. Okay. Let S be an oriented smooth surface okay, that is bounded by a boundary curve C with positive orientation let F be a vector field whose components have partial derivatives on an open interval open region, I should say, in R3 that contains S. If this is true, then the line integral of f dot dr is equal to the surface integral of the curl of f dot ds. Okay. So basically taking this line integral, right? Okay, C, and saying that if we have a positively oriented surface, okay, this would be n to our surface, okay, okay, then we can change the line integral of C to a surface integral okay, of S. This would be surface S. Maybe I'll make it look like, I don't know. That's fine. I mean, we could put we want this to be a surface, so let me get rid of this real quick. So if I went like this, it doesn't make sense. Let me redraw it. Let's just go like this. Make it simple. Okay, so here's my surface with C, positively oriented surface. Okay, boom, this is the top. Okay. Okay, and so this is n, my normal vector. Okay, line integral of C to a surface integral S. So my surface integral, just think of this as a surface. Okay, it's kind of hard because we're going to be referencing the line integral. Maybe it's hard to get a good picture here. Okay, so this would be the base, right? The base. Okay, inside. And then the rest of it would be kind of like my surface, right? So my surface. Okay, so that's my surface. Okay, and so we're looking at the surface S. Okay, so this curve C is the boundary for my surface S. And the other two, we can go backwards and forwards. We can go from a line integral of C to a surface integral of S, and vice versa. We can go back and forth between line integrals and surface integrals now. Okay. So number one here. Okay, evaluate C f dot dr, where f of x, y, z is equal to negative y squared I plus xj plus z squared k. And C is the curve of intersection okay, of the plane y plus z equals 2 and of the cylinder x squared plus y squared equals 1, so the unit cylinder. Okay, so and we'll say that C is the curve of this that has positive orientation. Okay, so we have this I don't know, this cylinder, this unit cylinder, 1, 1, 1, 1. Okay, so unit cylinder here. Okay. We're going to go up. Oops. Going to go up. Try to go up. Okay, and then we're going to intersect it in a plane. So, okay, so this plane is going to intersect this thing. Okay, so, and we're going to say this thing is positively oriented, which means it goes around counterclockwise, C. Okay, and we have this surface here. Okay. And so, okay, we have a force field, okay, with respect to this surface. Okay, and I'm going to say, hey, you know what? Let's find the curl of this thing and then evaluate it. Let's do that. Okay, so we want to take this thing, the line integral about this, and we're going to take this thing and turn it into the curl of f dot ds. Okay, so first let's find the curl of f. Okay, so I, J, K. Okay. Okay, and so we want d dx, d dy, d dz of negative y squared x and z squared. Okay. So cross off the first row, first column, and we get d dy z squared minus d dx x, oops, d dz, sorry, d dz x, which is, I thought the whole thing is going to go to 0. Okay, so that goes to 0. Okay, I minus j, this is going to be d dx of z squared minus d dz of y squared. That's another one that goes to 0. Z of negative y squared. J, that thing goes to 0. Okay, plus, okay, d dx of x minus d dy of y squared. Okay. Okay, so this becomes 1 minus 2y. Okay, so that's my curl. Okay, so if we look back here, okay, so how do we get the flux basically that we were talking about before? Okay, with the curl of that, right? Okay, so one second. Right. Okay. Yes. Okay, so the curl of S is this thing here. Okay. So let me make sure I'm using this correctly. Okay. So, yeah. We have an F, which is the curl of F ds, which we found the curl of F to be 1 minus 2y. Okay, I was thinking if there's a simpler way to do this, but I guess not. Okay, ds. S, right? And so what we can do is what we did in that homework problem, where we say that we're gonna parameterize this thing. Okay, where x is equal to x, y is equal to y, and z is equal to g of xy. Okay. So the projection of this thing the projection of the thing is just this disk. Okay, so D is this disk. D is the disk. X squared plus y squared is less than or equal to 1. Okay, it's just that disk. Okay, and so we did have this plane as well. Where'd that plane go? Okay, this one, y plus z is equal to 2. So this plane is y plus z equals 2. So if I solve this for z, y plus z equals 2, I get z is equal to 2 minus y. Okay. Okay, so we have, let's just write it like this. Okay, where we have the curl of f. You have to keep this in mind, that this is the curl of f. It's not f itself. It's the curl of f, okay, that we're looking for. So the curl of f is going to be equal to 1 minus 2yk. That's the curl of f. Okay, so when I do my partials, I have to think of, like, it's really this. It really is this. It's really 0I plus 0j plus 1 minus 2yk. And so, okay, if I think about p, q, and r, this is p, q, and r. P, q, and r refer back to the curl, not the original function. Okay, so you just have to keep that in mind. Okay. Where P, Q, and R come from the curl of f, not just f itself. Okay? So the curl of f is equal to this thing here. Okay. So this would tell me that this thing, which maybe I can make this another letter. I don't know. How about M? I don't know. M. Okay. Which is telling me that this thing, because there's too many f's, there's too many f's. It's telling me that this thing s, m dot ds, is equal to d over negative p dg dx minus q dg dy plus r dA. Okay. So, well, what's z in this case? What's g of xy? Well, g of xy is 2 minus y. Okay, that's it. 2 minus y. Okay, so if I take the partial of that with respect to x, I get 0. Right. So, and what is p? P is also 0. So it's kind of like negative 0 times 0. Okay. This is going to be 0 times, well, this is negative 1. Okay, plus r, p, q, r. R was going to be, r is my 1 minus 2y. Right, yep, 1 minus 2y. Was it 1 minus 2y or 1 plus 2y? Oh, it's a negative. It's a negative of a negative. So this is a plus, sorry. Because this is a negative y squared. My bad. Okay, so it's 1 plus 2y. 1 plus 2y. Okay, d. Okay, dA. Okay, so now, okay, we get this thing here of 1 plus 2y dA. Okay, but what's the double integral going to be? Well, it's along this disk, right? So if I have this disk here, I'm probably going to want to change it to polar coordinates. So let's change it to polar coordinates. Okay. So x is going to be equal to cosine theta, y equals sine theta, right? Okay. Let's make it r. Let's make it r. Cosine theta, r sine theta. Okay, let's just parameterize this thing into polar coordinates. Okay. Yeah. And then, so this thing becomes, okay, 0 to 1, and then 0 to 2 pi, because it's going all the way from 0 to 1, 0 to 2 pi. Okay, this is 1 plus 2 r sine of theta times r dr d theta. Don't forget the extra r there. So this becomes r plus 2r squared sine theta. Okay, integrate from 0 to 1, 0 to 2 pi. And this is dr d theta. Okay, so this is being r squared over 2. Plus, this is going to be 2/3 r cubed sine theta. Okay. And we're going to evaluate that from 0 to 1. So that's easy. This just becomes 1/2 plus 1/3, or sorry, 2/3 sine theta. Okay, evaluate that from 0 to 2 pi for d theta. So this just becomes 1/2 theta, evaluate from 0 to 2 pi, plus 2/3, this is negative cosine theta, evaluate from 0 to 2 pi. Okay, so plug in the 2 pi here, the 2 pi and the 2 cancel, that's leaving with pi. Plug in 0, you get 0. Plug in 2 pi here, this is negative, okay, negative 1, so this is negative, plug in 2 pi, you get 1. It says negative 2/3 minus, plug in 0, you get the same thing. It's just minus a negative 2/3. Those cancel out and give me 0. And so the answer is just pi. Okay. So going back to Stokes' theorem. Stokes' theorem. And we would say that this thing is equal to the integral of cf dot dr. That's correct. Okay, and that goes back here. Oops. Okay, and so instead of dealing with the function, we're dealing with the curl of the function. Okay. Those values. Okay, let's do one where we go backwards. Okay, number 2. Okay, use Stokes' theorem to compute the integral S curl of f dot ds, where, okay, f, so in this case they give us f, that's nice. F of x, y, z is equal to, oh, they give f in the other one too. Xz I plus yzj, yzj, okay, plus xyk. Okay. And S is the part of the sphere x squared plus y part of sphere, I can just say sphere, part of sphere x squared plus y squared plus z squared equals 4. That lies inside the cylinder x squared plus y squared equals 1, and above the xy plane. Okay, so what does this look like? Let's draw a picture. It's a sphere of radius 2, right? Okay. However, this piece does not exist because it lies above the xy plane, and it's in the cylinder. It's in the cylinder here. Oops. Let's draw the cylinder in a different color. Let's try that again. Okay, so my cylinder. Okay. Okay, so it lies below this, inside the cylinder, but below the, okay. Oh, it's part of the sphere. It's part of the sphere. It's just part of the sphere. Okay, so it's this part of the sphere here. Okay, it lies inside that cylinder. It's just this part. Okay, this is S. Okay, down here, this is D. That doesn't show up real nice. This is D down here. Okay. 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 Okay, so let's find C. The goal is to find is to find this guy here. So find C by finding the intersection of the cylinder and the sphere. Okay. So where do they intersect? Well, we got x squared plus y squared plus z squared equals 4, and x squared plus y squared equals 1. So I know that this thing is 1. 1 plus z squared equals 4. So z equals plus or minus radical 3. Okay, it can only be positive. So z equals radical 3. Okay. Okay, so at z equals radical 3, these things intersect. Okay, so C is equal to that circle, x squared plus y squared equals z of radical 3, right? Equals what though? Okay. Well, it equals 1. It equals 1, right? Because it's a cylinder, it's always going to equal 1. So it's always going to be 1, okay, because it's a cylinder. And at z equals 3, or z equals radical 3. Okay. So the integral of c f dot dr is equal to the integral of c of f of r of t dot r prime of t dt. Let's go back to a line integral. Okay, f r of t r prime r dot r prime of t dt. Okay, so what's r of t? We would say r of t. Okay. What is r of t? So we're going to parameterize this thing. Okay, in terms of, some sort of parameter. Well, we have this thing here, right? So what is x in the unit circle? How could we represent x as the unit in the unit circle? Okay, remember that c is not all of the area inside. C is only this line. Okay, oops. Again, too many colors. Okay, this line integral that goes around. Okay, this is C. Okay, when you're looking down, it'll look like this. Boom, down. Okay. Okay, this is C. Okay, it's just a line integral. So R of t, okay, it's going to be equal to the cosine of theta, okay, at I, plus sine theta j, plus radical 3 k. Okay, because we're going to be at that slice. Okay, we're going to be at the slice. We're going to be on the unit circle. But we're going to be on the unit circle, somewhere on the unit circle. Okay, on the unit circle, but we're going to be at a height of radical 3. Okay, so what's r prime of t? Well, r prime of t is going to be equal to negative sine theta I plus cosine theta j plus 0 k, right? Okay. Okay, so now I've got to dot these things together. Well, what's f of r of t? F of r of t. What was f again? F was xzi plus yzj. Xzi plus yzj plus xyk plus xyk. But we got to change all these to thetas. Okay, this really is r of. I mean, we can use t's if I want. I'll just keep it. Let's go back to t's. Sine of t. J. Cosine t, just to make it consistent. Okay, so what is x? X is cosine t. What is z? Z is radical 3. Okay, plus what's y? Y is sine t. Z is radical 3. Okay, and this is going to be cosine t, sine t. K, right? So this is j, I, j, k. J, k. Okay, so now what we want to do is we want to dot product this. So f of r of t dotted with r prime of t. Okay, so we want a dot product with the thing above it. Okay, so this is going to be cosine t, radical 3 cosine t, I times negative sine t, okay, plus, this is going to be radical 3 sine t times cosine t. That's kind of nice. Okay, plus cosine t of cosine t sine t times 0. Times 0, okay. So this thing becomes negative radical 3 sine t cosine t plus radical 3 sine t cosine t. Those are going to cancel. Plus 0. Everything cancels. So this becomes the line integral, okay, about c of 0, okay, of basically dt, right? So dt. Okay, but what is c? What were the parameters for theta? Basically, think of it in terms of theta. It was 0 to 2 pi. Well, the integral of 0 is 0. Okay, so the answer is 0. Okay, so so what's the curl? The curl of this thing more than likely would have been 0. Okay, or the integral of the curl would be 0. The curl would be 0, which could tell us some things about that surface.
When you take the integral of that, wouldn't it be 2t? Oh,
Say
wait, just kidding. Yeah, if you take the integral of, no, never mind. My mistake.
You could get a constant, but then, I mean, it's just going to subtract off anyway, right? So, okay. Okay, 16.9. Okay, divergence theorem. Okay, so we will define outward of solid regions as positive and inward as negative. Okay. Okay, the divergence theorem. Okay, let E be a simple solid region and S be a boundary surface. So we're just taking these concepts and we're going to go to the next dimension. Okay. Okay, let E be a simple solid region and S be a boundary surface of E with positive outward orientation. let F be a vector field whose component functions have continuous partial derivatives on E in an open region that contains E. Period. Then the surface integral of f dot ds is equal to the triple integral over the boundary region of E, okay, of the divergence of f dot dv. Basically, we're saying, look, we're taking the flux, okay, the flux to what we would call a hypervolume. Hypervolume being one dimension above volume. Hypervolume. Okay, fourth dimension. Okay, so we're taking flux, and we can go to the hypervolume or vice versa. Okay, recall, okay, that the divergence of F is equal to dp dx plus dq dy plus dr dc. Okay, that's divergence. Okay, number one. Oh, I didn't draw, like just think of this as like, you know, maybe something like this. This is E basically. E is a, okay, E is some volume in space. Okay, so this whole thing is E. It doesn't look good. Okay, this whole thing is E. Okay, E is a simple solid. Okay, and let S be the boundary surface of E. Okay, find the flux of the vector field F equals Zi plus Yj plus xk over x squared plus y squared plus z squared equals 1, the unit ball. Okay. So what do we want to do? We want to say, okay. So the flux of this is equal to this triple integral, okay, over this volume. Okay, integrating over the volume. Okay. So it's over this sphere, the unit sphere. The unit sphere is E in this case. Okay. That's what E is. E is the unit sphere. So we can say, okay. We're going to take this unit sphere, okay, and we're going to take the divergence of f, okay, divergence of f dv, and just do a triple interval. Oh, okay. So what's the divergence of f? Well, that's going to be, okay, d dp dx plus dq dy plus dz d, sorry, dr dz. So now, well, what's z with respect to x is just 0. What's y with respect to y? It's just 1. And what's x with respect to z is just 0. So this is just 1. So really all we're doing is finding, okay, what is the volume of this unit sphere? What's the volume of this unit sphere? Okay. Well, this is just going to be 1, right? And then I want to convert to spherical units, spherical coordinates. Okay, so I just need 1 times, this is going to be rho squared sine phi, d phi, d rho, d phi, d theta, d rho, d phi, d phi, d theta. Okay. So what does rho go from? Well, rho goes from 0 to 1. I can get rid of this one. And then it goes from 0 to pi, and then 0 to 2 pi. Okay. So what does this become? We'll integrate on rho. That's just rho cubed over 3. Okay. Sine phi. From 0 to 1, that's 1/3 sine phi. Okay, so then let's integrate with respect to phi. So this is negative 1/3 cosine phi from 0 to pi. Okay. So then this becomes cosine of pi, which is negative 1. So this is negative 1/3 of negative 1 minus negative 1/3 of 1. Okay, so this is just positive 2/3 or positive 1/3 plus 1/3, which is 2/3. Oh, okay. So that's just 2/3. Okay, and then what do we want to integrate that from 0 to 2 pi d theta. And so this just becomes 2/3 theta evaluated from 0 to 2 pi. And so plug that in. That just becomes 4 pi over 3, which is the area of the unit sphere. I already knew that, right? Because what's the area of a sphere? 4/3 pi r cubed. And what was r in this case? Well, r was 1. So I didn't really have to do this. It was kind of nice to do it in spherical coordinates, but I didn't really have to. I could just said, hey, you know what? The area of a unit ball, or the area of the volume, this is volume. I know I'm saying area. This is volume. Okay. The volume of a unit sphere, okay, is 4/3, 4 pi over 3. Okay, which in this case was the flux of this vector field. Okay, over this. So that was the flux. Okay, that equaled the flux. Okay, F ds. Okay, it was that surface integral. Okay. Okay, let's do this backwards. Okay. Let's do number 2 here. Okay, evaluate. Okay, S F dot ds, where f of x, y, z is equal to x, y, I plus y squared plus exz squared j plus sine of xy k. Okay, and S is the surface of the region, okay, bounded by the parabolic cylinder z equals 1 minus x squared, and the planes z equals 0, y equals 0, can't draw my zeros today. Okay, y equals 0, and y plus z equals 2. Okay. Okay, so what does the surface look like? Okay, region bounded by the parabolic cylinder. Z equals z equals 1 minus x squared. Okay, so 1 minus x squared. Okay, so when okay, this is just going to be negative x squared plus 1. Okay, so this is 1, right? When x is 0, z is 1. Okay, when x is 0, z is 1. And then when x is 1, z is 0. It goes down like this. Okay. Okay, and then what happens in the y direction? Well, nothing. I mean, you can just keep going on forever. Right, it's a cylinder. Okay. But we have a z equals 2 minus y is the plane that we're looking at. Okay, so this plane is gonna slice and dice this thing. Okay. So what does this thing look like that it's slicing and dicing? Okay, when y is 0, z equals 2. When y is 0, z equals 2. And when z is 0, y equals 2. So go out infinitely in the x direction. So x can be anything I want it to be. Okay, nice. X can be anything I want it to be. But this is the plane. Okay, so x, it's going to be in, the plane's going to be in the x direction because x can go anywhere. Okay, and so when y is 0, yes, I like that. Z is equal to 2. Oh, okay. So z is equal to 2. And when x is and when y is 2, z is equal to 0. Okay, so keep this in mind here. Okay, if I have this guy here, I don't like the way this is drawn there. Yes. Can't draw it today. Okay. And so this thing's going to slice right here. So let's look at the slicey slice. Slicey slice, because it's going to come down here. And it's going to slice, right? It's going to come over like this. It's going to give me a nice slice. Sliceroo. Give me a nice slice there. So it's going to come around like so. And it's going to slice at an angle. It's going to slice this off. This thing doesn't even exist. None of this exists. None of this, none of you, sir. You, sir. You, sir, do not exist. Goodbye to you, sir. Goodbye. Hasta mañana. Okay, actually, no. I won't see you tomorrow. Won't see you later. Okay, boom, boom, boom. Get rid of my auxiliary lines here. They don't do anything for me. Okay, makes sense. Nice. Nicely done. Nice. Okay. So that's the niceness. Okay, so we've got this thing here. And we want to know, okay, so how do we find the surface integral of this thing? Okay. So, okay, well, the surface integral is going to be equal to the triple integral of the divergence dot dv. Okay, so the triple integral of this thing. Okay, so what is dv? What's the divergence of f? Well, the divergence of f, okay, is going to be this thing with respect to x. Okay, so that thing with respect to x is just going to be 1, right? No, it's just going to be y. This is going to be y. Okay, plus. Okay. Okay, this thing with respect to y, ooh, that's just going to be 2y plus. And then this thing with respect to z, well, that's just 0. That's 0. That's 3y. Okay, so the triple integral, okay, over this volume, okay, 3y, okay, dz, dy, dx. Okay, so now I have to ask ourselves, what are x, y, and z going from? I want to get my limits here. What are x, y, and z going from? Well, let's see. What does x go from? It looks like x is going from -1 to 1. Okay, I'm going to say that x goes from -1 to 1. Okay, from my diagram, -1. That's why I spent so much time on this diagram, just to get it wrong here, is so that I could really analyze what this three-dimensional region is, what this volume is. Okay. What this solid, I should call it a solid. What is this solid here? Okay. Okay. Nice. Okay. Let's see. What's z going from? Z is going from, looks like 0. Okay. 0 to, no. It looks like it's 1 minus x squared. Wouldn't you think? 0 to, right? Because that's the top of the thing, right? The top of the thing is 0 to, thinking, no, I think you're right about that. Let's because I need to get down a variable each time I do this, right? So let's go to y first, because I want y in terms of x. I just want y in terms of x. Okay. The problem is I can't do that, is I have y in terms of z. So you know what I'm going to do? I'm going to be sneaky here. Okay, I have y in terms of z, and I don't have y in terms of x. So I'm going to reverse I think I'm going to reverse my limits of integration. Because I want y in terms of z. Okay, I want y in terms of z. And then I want z in terms of x. Yes. Okay, so I want y in terms of z. Y in terms of z. I want y of z. Y in terms of z. Okay. And then z goes to x. So yeah, I got to swap these two. I got to swap those two. So x can stay there. Okay, but I'm going to swap these two. dy, dz. Oops, I already have a z. A d. Okay, y. So what is y going from? Y is going from 0, okay, 0 to the plane. Okay, if we think in terms of, so 0 to something in terms of z. Okay, 0 in terms of z is 2 minus z, 2 minus z. 2 minus z. Okay, let me think about this for a second. When I probably could have done this. Oh, I probably could have done this in terms of x and y, but that's okay. Okay, it's just because this thing is going off in the y direction. Okay, makes it a little bit more complicated. Okay, but again, if we think of it in terms of this in terms of this. X and z, right? Okay, this is 1 minus x squared. Okay, that's that guy. So this thing goes from 0 to 1 minus, yeah, x squared. Okay, yeah, and y goes out further. Yeah, makes sense. Okay, so yeah, y, and then this is going to go from 0 to 1 minus x squared. Okay. Yeah, you can keep eliminating a variable. Exactly. Okay. Well, that's good. Okay, so now I'm going to integrate on y. So this is 3 halves y squared from 0 to 2 minus z. Okay. Okay, plug that in. We get 3 halves times 2 minus z squared. Okay, integrate that from 0 to 1 minus x squared dz. Okay, so now we've got everything in terms of z. Okay, and so this is going to be negative. So this is going to be 3 halves 2 minus z to the third over 3 times negative 1, right? Because if I did a u to u, I'd get a negative 1 there. Okay, evaluate it from 0 to 1 minus x squared. 3's cancel. So I'm left with negative 1/2. 2 minus 1 minus x squared cubed minus a negative 1/2. Okay, negative 1/2 times 2 minus 0 cubed Okay, so this thing is going to be 2 minus 1. So this is 1 plus x squared cubed. Negative 1/2 plus, this is going to be 8. So 8 divided by 2 is 4 plus 4. Okay, so integrate that from a negative 1 to 1 dx. Okay. So I'm going to multiply this all out so I don't have to do a u sub and not get an x. If I do a u sub on this, I don't have the du. So I'm going to multiply it all out. So I can just use the power rule. So cubing this out, okay, so this is going to be 1 plus 2x squared plus x to the 4th. That'll get multiplied by negative 1/2 and add to 4. Okay, so this is negative 1/2 minus 3/2 x squared minus 3/2 x to the 4th minus 1/2 x to the 6th plus 4. Okay, so let me put this in descending order. Negative 1/2 x to the 6th minus 3/2 x to the 4th minus 3/2 x squared plus 7/2. Okay. And we still want to integrate this from negative 1 to 1 dx. Okay, and so this becomes negative 1/14 x to the 7th minus 3/10 x to the 5th minus 1/2 x third plus 7/2 x from negative 1 to 1. These are all even. I mean, they're all odd powers, okay, which means that they're all going to be minus a negative, which is going to be a positive. So it's just going to be double this. Because they're all, I could plug in 1 and just double the whole damn thing, and then it should be good, but whatever. We can see. Okay, so 1. So plug in 1 for this whole thing. It's just negative 1/14 minus 3/10 minus 1/2 plus 7/2, right? So this is 3. Okay. This is 3/10. Okay. Well, this is 3. And this is going to be 70. So I think this is 70 as the common denominator there. So 70. So this is negative 5/70 minus 21/70. Okay, plus 3. This is going to be negative 26/70 plus 3, which is going to be 2 and 44/70. Multiply the whole thing by 2. Which I don't know what the hell that is. This is going to be 184 over 70 times 2. Cancel it out, we get 184/35. Okay. Yeah. Okay, that's it. So we're done with the course, except for the last two exams. There is no, since I covered both 16.8 and 16.9, there is no class on Wednesday. So class is canceled on Wednesday. Okay. I'll see you Monday for the review. Bye. Happy Thanksgiving.
Thank you, Professor.
Bye. Thank you.
Thank you, Professor.